Hi, I am Mehraveh Javan and welcome to the presentation of our work, Balanced Mixture of Supernets for Learning the CNN Pooling Architecture. I'm going to start by presenting some background and motivation for our work. In a typical CNN, several downsampling layers are often used to reduce feature map sizes, and they are usually performed by either max pooling or strided convolution. They are important because they reduce the computational cost of the CNN and control the information that is passed through the network. The problem of finding optimal pooling configuration can be cast as a neural architecture search or NAS problem. We can separate current NAS search spaces in two groups. The first one contains early NAS work and some recent work, and they try to search for the entire network architecture. Although it's more global search space, it often requires high computation. The second group only searches for the operations inside the layer and fixes the skeleton of the network. This search space has become very popular in recent years because it's more efficient, and many influential works such as Darts and Toews work in this search space. However, this search space is limited and excludes the pooling configuration. Some works outside the NAS framework also try to tackle the problem. However, they often require replacing downsampling operations, complex operations, and continuous feature maps or kernels. The next search methods that we will discuss in our work all use the concept of weight sharing or Supernets. To briefly explain it, a Supernet contains all the possible architectures in the search space. It is trained using a NAS method, such as Dart, and then sampling a path in this supernet will result in sub-supernet or candidate architecture. These candidate architectures inherit the weights from the supernet and are then evaluated and ranked, and the best one among them is chosen as the final architecture. Since the candidates don't need any retraining, the weight sharing is very efficient. We are also going to briefly revisit Dart, or differentiable architecture search. Dart relaxes the operation in the search space with softmax weighting, which are then trained by backpropagation. The operation with max weighting is then selected for the final architecture. Because of this relaxing, and because we can perform the search with gradient descent, Dart is very efficient. However, because the backward pass is performed through whole supernet, it has high memory requirements, and furthermore, it's biased towards more sampled architecture. Another influential work is the single path one-shot or SPOS method, and it has the benefit of lower memory requirements because it only samples one path and performs backpropagation through it. And also because it performs uniform sampling on architectures, it reduces the bias. However, all this work use the weight sharing, and the issue with the weight sharing is that it generally suffers from poor rank correlation between the evaluation at the end of the training and the ground truth. And this is because of the coupling of the weights among architectures. One of the proposed solutions is reducing the weight sharing by reducing number of architectures that share weights. In this regard, some works that are related to our research propose to partition the search space into sub-supernets. But these works usually perform this partitioning by either randomly or manually. Now we discuss the methodology of our work. We start by defining the search space. Considering a default CNN, We fixed the number of layers and channels for simplicity, and we only search for the pooling locations in this backbone architecture. We also applied certain conditions. We fixed the first and the last feature map sizes, and we applied two additional constraints. One is that feature map sizes cannot increase throughout the network, which is reasonable for classification tasks. And the second is that at most one downsampling is allowed per layer. Now we start our experiment with a ResNet 20 backbone architecture on a C410 dataset. And this is a relatively small search space of size 36. For two architectures in this search space, we test both the standalone accuracy and accuracy using weight-sharing. And unsurprisingly, we see that the weight-sharing reduces the accuracy of both, confirming that less weight-sharing can be beneficial. With this in mind, we propose a new method, balanced mixture of Supernets, to reduce the weight-sharing automatically. Instead of using just one Supernet, we propose to use a balanced mixture of M Supernets, or as we call it here, MOB. We start by uniformly sampling the configuration, as is done in a SPOS. We then sample a model based on the conditional probability, and then perform one batch of training and one batch of validation. The validation accuracy is then used to update the probability matrix, also to ensure that the model selection is not biased towards more sampled models. We renormalize the model probabilities in its epoch to be uniform. Now, we can see here if we have 4 models, we start by a uniform probability matrix. And as we progress through the training, we can see that the models are specialized for the architectures. Now we perform many experiments with our methods. We started by establishing a benchmark by training all configurations in our search space, as shown on the table on the left. The architectures here are shown by number of layers per feature map size. And we can see that the default pooling architecture is not necessarily the best. And by only changing the pooling, we can improve the performance. On the right, we show the correlation between the evaluation accuracy and the ground truth for different number of models. And we can see that increasing the number of models improves the correlation as well as rank correlation that is shown by Kendall-Tong metric. And furthermore, we see that higher performing configurations benefit most from increasing number of models or F. We did comparison with both NAS and non-NAS methods. For all the NAS methods that we tested, we performed better than them. And also DART and its variant, final architecture, was not reasonable for a classification task, and that was because we could not easily apply the constraints to DART. For non-NAS methods, we either performed better or had similar performance. Finally, we tested our method in larger search space and more challenging datasets. Our tests on ImageNet indicate that the initial pooling configuration may have been heavily optimized manually, and it was the best configuration that we found, and we were able to recover it with only 2 models. For Food 101, we showed that the performance increases proportional to the number of models. Finally, to summarize our work, we cast finding pooling configuration as a NAS problem, and we showed the effects of pooling configurations on the performance of CNN. We also showed that common NAS methods, such as DART and SPOS, fail to solve this problem, and we attributed the problem to the weight sharing problem. To remedy this, we propose balanced mixture of supernets that reduces the weight string automatically, and it results in improved rank correlation with ground truth and better final architecture. And we tested our method on several datasets and several ResNet backbone architectures. Here are the relevant layerings and view references, and thank you very much.